Hi everyone. In this video, I'm going to explain how we create a customized linked list or custom built linked list using the node class. We've seen the node class in our previous video. It contains a reference to the next node and some data, in our case, an integer. It has your usual getters and setters and a parameterized constructor to which you need to pass both the data and a reference for the next instance variable. In the custom linked list, all we need to store is a reference to the first node in the list. And these nodes will be linked to each other, creating a linked list. The first method that we'll see is adding an item to the front of the row, to the front of the list. Now that's a very nice and compact method, but it can be a bit confusing, so I'll explain it using some examples. What we do is we create a node object, and let's call this node object new value or new node, or let's call it n. So we create a new node for which data value is value and next value or the next reference is head. Now you'll see how it beautifully works whether the list is empty or not empty. And the second and more important step is we re-refer head to the newly added node, because that newly added node is now the first node in the list. So how this will work is like this. When we create a new custom linked list object, list is an object that has only one instance variable, head, but in the default constructor, head is null. When we add an item 6 to the front of the list, we are calling this method over here. It creates a new node with value 6, and the node reference is head, which is currently null. So here we are creating a node object which refers to a block of memory where data is 6 and next is null. In the second step, we re-refer head to node. So instead of head being null, head now refers to this object. When this method finishes, the local variable node is destroyed, which is fine because we have the node added to the list in reference head. When you call the method again with add to front 15, let's see what happens over here. You call the method, and inside the method you create a node object which refers to the instance variable where data is 15 and next is head. Next is head, but what's head? Head is this node, this reference over here. So next refers to this node over here. And then we update our head, which means head doesn't refer to the old node. Now head refers to the newly added node. When the method finishes, the function scope variable node is destroyed, which is fine because head holds a reference to the now first node, and the first node holds a reference to the second node, and the second node holds a reference to null, which means it's finished. So effectively speaking, a cleaner diagram becomes list holds a reference to head, which holds a reference to data 15 and next holds a reference to a node where data is 6 and next is null. You can also write it in a more compact manner as data is 15 and then data is 6 and then it links to null, and you can label the first node as head. So what we see over here is this is a more detailed diagram, while the second one is a more compact diagram, and we use this diagram more often than the other one. We'll write another method now which returns how many nodes are there in the list. Since we need to return the size, we initialize a counter. We also initialize the current node as head. So we start with the head, and as long as the current node is not null, we keep going forward, but every time we go forward we increase count by 1 and then move forward by saying current becomes current.getNext. Eventually current will become null, and it's at this time we return count. Let's see how this will work for a typical list. Let's say the list is 20, 50, 30 and 10 referring to null. This is the head of the list. On line number 11, count becomes 0. On line number 12, current equals head, which means current refers to the same node as head refers to. While current is not null, yes, current is not null, the loop enters, count increases by 1, and the most important thing is current moves forward, because current becomes current.getNext, and the old current.next refers to this node. Again, the loop expression is checked on line number 13. It's still not null, so again count increases and current moves forward. It's still not null, count increases, current moves forward. Still not null, count increases, current moves forward, and now it has become null. It's at this stage that the loop stops executing and the method returns 4. Instead of size, if you needed to add all the values together, you could do something very similar, but this time instead of count we rename the variable to result, and result needs to become whatever it is already plus current node's data value, and we return result. Again, let's see how this is going to work. For this example, let's take a different set of data. Let's say the data is 2, 5, minus 3 and 0. Current starts with head and result is originally 0. It checks that current is not null. Result increases by increases by current dot get data, which is 2. So result becomes 2. And current becomes current dot get next, and the next reference refers to this node over here, which means current moves forward. Again, current is not null, so result increases by result dot get data, and current moves forward. Result increases by result dot get data, which is minus 3, therefore it becomes 4, and current becomes current dot get next, It's still not null. Result increases by result dot current dot get data, which is 0, so it remains 4, and current becomes current dot get next, which is now null, and the loop finishes with the final result equals 4, and that's our answer. Another variation, instead of adding all the values, I might want to add all the odd numbers. Here we have to check if the number we are at right now, which is current.getData, is in fact odd. So its remainder by 2 should not be 0. Only then we add current.getData to result, which means this time it will traverse each value one by one, but before adding it to the result, it will check if it's an odd value, which it is not. Then is this an odd value, which it is, so result becomes 5. Minus 3, it is, so result becomes 2. 0, it is not, and result is 2, which is 5 plus minus 3. So those are some examples of how to traverse a list in a very standard way. We'll now describe 3 very important methods, the first being get an item at a specific index. So what we are trying to return in this method is return the value, which is data component of the node at supplied index. Of course, it's possible that the index is invalid, in which case we should return null, and therefore the return type cannot be int but integer object. Return null if index is invalid. So how do we know that the index is valid? First of all, you can see in the previous example, when you have 4 nodes, valid indices are 0, 1, 2, and 3, which means valid indices are more than equal to 0 and less than the size of the list. In this case, 3. Size minus 1. Size is 4, therefore it should be less than size, which means if index is less than 0 or index is more than equal to size, it corresponds to an invalid index and we return null immediately. If we come over here, it means that the index is valid, which means we can move forward required number of times and fetch the data from there. So for int I, we start node current is head, start from the first node, index number of times current moves forward, and then when the loop finally finishes, we can return the data value at the current node. Let's see how this will work with our example. Let's say the index passed is 2. 0, 1, 2. So it should return minus 3. It will start with current equals head, and I is 0 till I less than index, which is 2. So it will 0 is less than 2, so current moves forward. I increases by 1, 1 is less than 2, so current moves forward. This time I is 2, and is 2 less than 2? No. So you can see that we moved forward twice. And now the loop finishes, and what we return is current.get data, which is -3, which is the value at index 2. If the value passed for the index is 0, if index is 0, I is 0 and 0 is not less than 0. So current never moves forward in that case. So when index is 0, it correctly returns the first item from the list. So that's accessing an item from the list, which, as you can see, requires a loop to be traversed and is order n, because the further is the item, the more times loop executes. The second method is to insert an item at a random, not random, but arbitrary index. So the return type is void, apologies. What it's trying to do is add the item at supplied index. Again, we'll see where can the item be inserted. This time the item cannot be inserted at a negative index, or the item cannot be inserted at more than size. Please note that we can insert the item at index size. In this example, we can insert the item at index 4, and the item will be inserted after the last node. So if the index is invalid, we don't do anything, we return immediately. We construct a node with the required item, and next is null. If IDX is 0, that's a special case, because we are trying to add the item in the front or at the front, but we've already written that method, so we can simply call that method add to front that item. So probably I can delay constructing the node till here. Otherwise, it means that index is more than 0 and we have to insert it somewhere in the middle or at the end. We start current equals head, and we'll move forward the number of times, which is index as well. So for int I equals 0, I less than index I plus plus, current becomes current.get next. Now what's going to happen is, if, let's say, hypothetically speaking, index is 2, let's say the item that we are trying to add is 7 and index is 2. We've already seen that this given loop moves forward index time, so it will move over here. We are trying to add an item here. So the problem is that we are trying to add an item, in fact, between 5 and 3. So we should be moving current forward index -1 number of times, and I'll simply add -1 here. Now this will mean that we have a node constructed already, which has the data value 7, and we have a reference to the current node here. We are trying to insert our node after the current node, but before the connected node. So first we link our new node to the node after current. How do we do that? We say node dot set next to current dot get next, which means after the node that we are adding should be the node that is currently after current, which is the node containing -3. So this link has been established. This link has been established by node.setNext current.getNext. Now second, we need to remove this link and instead have that link going here. And we can do that using current.setNext to node. So it breaks the link between current and the node currently after current and creates this link. And you can see how it makes my linked list as 2 followed by 5 followed by 7 followed by -3 followed by 0 followed by nothing. Now the beauty of this code is that it works correctly even if you're trying to add an item at the end of the list. So let's say my list is 2, 5 and 30 at indices 0, 1 and 2. The item that I'm trying to insert is 12 at index 3. We construct a node with item 12. Our loop executes index -1 times, which is twice. Moving current once here and second time over here. On line number 79, node.setNext current.getNext. Node.next becomes current.next. Now what's current.next? Current.next is null. So node.next also becomes null. And on line number 80, current.setNext to node. So current, instead of referring to null, now starts referring to node. And you can see that this node is added to the end of the list. The last method, the third and last method, which is very useful, is to remove an item at an index and also return the removed value. Again, return the value of the node removed, value inside the node removed. We first check for bounds. If index is less than 0 or index is more than equal to size. This time it's more than equal to size because there's no value at index size. We immediately return null. So maybe specify that here as well. Return null if invalid index. Remove the item at supplied index and return the value removed. Next, again, in this case, what we have to do is move forward index -1 times, which means start from current equals head. Same loop, again, move forward index -1 number of times, which will mean if I need to remove the item at index 2, we are moving index -1 times. So we are moving once only in this example. So we move forward here, and what we are trying to do is change this reference instead of 5 referring to 30, because 30 is the node that has to be removed. We can say current.setNext to current.getNext, which is this node, dot getNext, which is 12. So we are trying to re-refer current.next to this node. But before we re-refer, because as soon as we re-refer, this node will be lost, and since this link will be lost, and since the node is unreferenced, the node will be deleted along with its outgoing references. So what's important is, before we change this link, we need to store the value that needs to be returned into a variable. So let's do that. we can say int result is current dot get next, which is the node to be removed, dot get data. Now that we have the result in a variable, we can modify the reference for current dot next. We can say current dot set next to current dot get next, which is the node to be removed, dot get next. This means current stops referring to this node and instead refers to the node at current.getNext over here. Since this node is no longer referenced, it is deleted from the memory, and you can see the node at index 2 is removed now. In the end, we have to return the value removed, which is result. This code works very well for the last node as well, so let's take an example of that to be completely sure. Again, we'll say the nodes are 2, 23, and 71. Now, the node to be removed has index 2, so it's this node to be removed. Current starts from head and moves forward index minus 1 times, which is 1 time. We store current.getNext.getData into result, which means result becomes 71, and then current.setNext, so current.next becomes current.getNext, which is this node, dot another getNext, which is null. So current.next refers to null. Since this node containing 71 is unreferenced, it's erased from the memory along with outgoing references. We're going to write a very quick, we'll write one more method, which is toString, public string toString. It should return the entire linked list's string reference. We start with a square bracket. For I equals 0, I less than size I plus plus, which means for each item of the list, or you can traverse it using current. Either way is fine. Start from head. As long as current is not null, keep moving forward, but this time result becomes result plus whatever current contains plus a comma space, and move current forward. Remove the last comma and space from the result and add a closing square bracket to it and return the result. So it's nice for creating a client. We'll now create our custom linked list client. Create an object. One thing that I forgot in the toString method is if head is null, return empty list representation. So we'll display list. So it should display square brackets, empty square brackets. And there it is. Let's move it here so it's a bit more visible. Empty square brackets. Then we add item 20 at index 0. So it should be added at the front of the list. We display the list again, and it's become 20. Cool. We add the item 30 again at the front, so it should become 30, 20. Correct. We add item 40 at index 2, which means at the end of the list. 30, 20, 40, perfect. We add another item 50 at index 1, which is after 30, 30, 50, 20, 40. We add another item 20 at index 8, which is invalid, so nothing changes, which is correct. Adding an item at index -1 will also not do anything. There are 4 items right now. Let's add a few more items at index 4, which is again at the end of the list, and let's make it 7. So the item has been added to the end of the list. Now we can start removing items, or let's display item at specific indices. Let's display the item at index 2, which should be 20. The item at index 5, which should be 70. At index 4, which should be 70, and at index 0, which should be 30. So we should get 20, 70, and 30. There they are. Let's display list.total. It's 210, correct. Now let's start removing items from the list. Let's display the item removed from index 0 and then display the list. So we are trying to remove the item 30 and the list becomes 50, 20, 40, 70. So there's a problem clearly. Remove 0, remove the item 50, which we didn't want to. So there is a bug in my method. Let's take a look at that. Clearly there's a bug because when index is 0, it's a special case. We are trying to remove the first node, which means if index is 0, result is head.getData, and head becomes head.getNext. So, and we return result. So removing the first node is a special case. Let's run this again, and this time it works correctly. Now there are 4 items. Let's remove the first item again. You can see 50 is removed and the list becomes 20, 40, 70. But instead of removing the first item, let's skip that. So 50 goes back. Instead of removing the first item, let's remove the third item at index 2. So we're removing 40. The list becomes 50, 20, 70, and the item is returned to the user. Again, remove the item at index 2, which is the last item. So 70 should be removed, and list becomes 50, 20. That's how a linked list is created, and I hope you guys benefit from this video. Thank you very much.